Hello. So, well, guys, in our previous class, we were discussing about few properties of Hilbert transform, wherein our very first property says that a signal x of t and its Hilbert transform have same magnitude spectrum. So that is, if I consider any signal x of t and its Hilbert transform, that which can be got by passing the input signal x of t via Hilbert transformer. So here I'll get x cap of t. So we represent Hilbert transform with this cap symbol. So over here, we all know that Hilbert transformer impulse response h of t is equal to 1 by pi t, or its transfer function h of f is equal to negative signum function of f. So we have been through all these mathematical concepts, how we ended up with this impulse response equal to 1 by pi t, as well as how exactly its transfer function h of f is equal to negative j signum function of f. So here this h of t is in time domain. Only thing is we are trying to speak the same thing in two different domains. So here this is in time domain, and this part, that is transfer function h of f, is the same thing, but the only thing is this is in frequency domain. So that's the only change. We are trying to refer on to a same person by using two different names. So if I think of a person, now thing is he'll be called by a different name by his family members, or whatever name his parents keep, he'll be called by that name in his family, as well as we can refer on to the same person. So because friends will be calling names, so here, in fact, we are referring on to a same person, but the thing is using two different names. So likewise here, we are trying to refer on to this Hilbert transformer. So where its impulse response is h of t. This is in time domain. And the same thing in frequency domain is negative j signum function of f. Okay. So, so this is the property number one, where magnitude of negative j signum function of f is equal to 1 for all the frequencies. So here if we put magnitude on, if I make modulus operator on both sides. So here we'll get its value as equal to 1. So we'll be getting 1 for all the frequencies. So thereby x of t and x cap of t have same amplitude spectrum. So this is our property number 1. And in property number 2, if x cap of t is Hilbert transform of x of t, then Hilbert transform of Hilbert transform is negative x of t. So in our previous class, we were discussing somewhere here, we were into property number 2. So now let's take up this property number 2 and discuss it in detail. Bhargav, is there any problem? Guys, is there any problem? Is the screen visible or not? Guys, If there is any problem, do let me know. Okay, well. So right now let's discuss our property number 2. And this property number 2 states, we all know that x of t represents Hilbert transform of input signal x of t. Now, if I apply one more Hilbert transform onto this, if I apply, so if I take one more Hilbert transform over here, so it's like passing the signal. It's like passing the signal. If I think of x of t to be my input signal, it's like passing this input signal x of t via two such Hilbert transformer block. So here, what was my initial input signal? It's x of t. So this is my input signal. And here, what is my intermediate output signal that I'll get over here if I make this x of t to pass through this Hilbert transform? I'll get it as x cap of t. Now this intermediate output, when made to go through one more Hilbert transformer block, I'll get output signal as x double cap of t, because Hilbert transform operation is represented as cap. So here we'll have x double cap of t. So this is the meaning of x double cap of t. Now let's see what is this actually equal to. Let's see what is this actually equal to. Now, if I rewrite, okay, now what I'll do is I'll try to replace this Hilbert transformer with its transfer function, and we all know that it's given as negative j signum of f. So this is the transfer function of first block. Likewise, the other block is negative j signum function of f. And let's assume that I'm passing input signal in frequency domain x of f. Now, you might have studied in your control system subject. You might have studied in your control system course that if there are any two systems having gain G1 and gain G2, that which are cascaded together like this, where this is my input and this is my output. So what happens to the overall gain? This is equivalent to, again, input signal. I can combine these two cascaded blocks into a single block whose gain is equal to G1 into G2. I can do this. Likewise, here I'm having two such Hilbert transformer blocks. All I can do is I can multiply these two. Such that negative into negative will have what we'll have. What is negative into negative? Positive. Here I'm having j, one more j on other block, so I'll have it as j square. And again over here, I'm having two signum functions. I'll have signum square of f. So this is x of f, and this is x cap of f. Now over here, pay attention. Now here I'm having j square. Now tell me, what is this j square equal to? Can I have some answers in the chat? What's the value of this j square? -1. Yes, correct. The value of j square is 1. So it's equal to 1 because of the fact that this is because j value is what? J is imaginary number that which was used to denote square root of -1. So here if I square it, I'll have it as equal to -1. So j square is equal to -1. So let me substitute that -1 over negative sign, just negative sign over here. Negative signum square of f. And what is happening to this signum square? So, what was the signum function actually? So we all know its shape. How exactly it behaves? Signum function of f can be thought of as equal to +1 for frequencies greater than 0, and the signum function equal to 0 for f equal to 0, and it takes amplitude value -1 for frequency lesser than 0. So this is signum function, or graphically we can denote it as, so this is signum function. So it takes amplitude value +1 for frequencies greater than 0, and for negative frequency, that is f lesser than 0, it takes the amplitude value -1. So this is for f greater than 0. So this is signum function. But am I having just signum function over here? No, it's signum squared. So when I square this, what happens? Anyhow, positive value. If you square 1, +1 square is +1 itself. But whereas the amplitude for negative frequency, that which is -1 square. So if I do this, I'll have +1. So in fact, signum square of f is equal to, it takes on +1 value for all frequency values, be it positive or negative, be it f greater than 0 or f lesser than 0. So in fact, we'll have this horizontal line parallel to frequency axis whose amplitude value is equal to 1. So you can see that this block that which is associated with gain value signum squared of f, and here we know that signum squared of f is as good as what? It's equal to amplitude value equal to 1. So in fact, can I replace this signum squared function with its magnitude value? Because all we are right now interested is in its magnitude value. So in fact, we can replace this signum squared with just minus, what is signum squared amplitude value? +1. So here negative into positive will have again negative value itself. So this entire thing is what? -1. So in fact, this negative sign will reflect at our output. So x cap of f over here. So it's not just x a single cap. Wait a minute. So here, because I have combined these two, so it was basically, so here it's x double cap of f. So here one more cap over here that I had left, x double cap. So in fact, this x double cap of f is as good as negative x of f. Or if I apply inverse Fourier transform, I'll get it as small x double cap of t in turn equal to x of t. So this is the general case. This is the general case. So this is how we can prove the second property of Hilbert transform, that which says Hilbert transform of an Hilbert transform is as good as negative x of t. So let's take an example. Let's take an example and try to prove this. Let's take an example case where let's assume some value for x of t, where we'll assume some value for x of t. So right now, let this input signal x of t be equal to some cosine function, cosine omega t. So this is the thing. Now, what we are supposed to do if I'm supposed to find x double cap of t? So what should I do? We all know that Hilbert transformer block, what it actually does, it does bring in plus or minus 90-degree phase shift for frequency components, for frequency component of input signal. Now the sign of this plus or minus 90-degree depends upon the frequency value. It depends upon what? The frequency value. That is, it will be positive 90-degree. It will be positive 90-degree for. So let me redraw this negative j signum function of f. Negative j signum function of f. So where this is how it looks like. This is positive j and this is negative j. So it changes the phase of, so it changes the phase by 90-degree for all negative frequencies, or it multiplies, or in other words, if I were to, I can also put it as it changes its phase value by negative j for positive frequencies and positive j for negative frequencies. So this is what is it's trying to do. So here j means, here I can think of it as positive 90-degree and here I can think of it as negative 90-degree. So, or in other words, it changes the phase by negative 90-degree for positive frequencies and positive 90-degree for negative frequencies. So if I were to analyze it in time domain, I can think of x of t to be equal to cos omega t minus 90-degree. But here is a problem. We cannot strictly say whether it's, so let me, okay, here bracket should have been at this place. Okay. So x cap of t can be thought of this, but we don't know where exactly this cosine function is starting. So we cannot exactly say whether it's positive 90-degree or whether to substitute cos omega t plus 90-degree. So analysis in time domain is quite confusing. Analysis in time domain is confusing. So what should I do? So in order to solve this, let's look at the same problem. Let's look at the same problem in other perspective. Because any problem cannot be solved by looking at a single perspective. It should be looked, if you are not finding solution for that problem, you got to change the direction in which you are trying to visualize it. So if that is not getting solved in time domain, then obviously we are supposed to jump to what domain? The other domain, that which is frequency domain. And in order to jump from here to here, what am I supposed to make use of? I am supposed to make use of Fourier transform. So you have already studied this Fourier transform, but let me tell you, this Fourier transform is very, very important, because even though it's not closely associated with Hilbert, like even though Hilbert transform is an entire independent topic, but Fourier transform is essential for this. So if you want to know this Hilbert transform, you are supposed to, the prerequisite of this Hilbert transform is this Fourier transform. Okay. Now let's apply Fourier transform. So initially we had the signal x of t equal to cos omega t. Now if I apply Fourier transform onto this, if I apply Fourier transform onto this as well as onto this, so we'll have capital X of f. So cosine in time domain is like this. It starts at angle 0 where its amplitude will be 1, and at 90 degree it reaches 0. So this is one full cycle. This is one full cycle. This angle is 2 pi radian or 360 degree. So this is cosine function cos omega t. So the same cos omega t in frequency domain will look like this. Right now it will be a function of f. We all know that Fourier transform of cos omega t is equal to half delta f minus f naught plus delta f plus f naught. So we all know this. So it can be represented as an impulse function. It is nothing but impulse function. The only thing is this impulse function right now, this, if I take up my very first impulse function, f delta of f minus f naught. So what is this? Impulse function, we all know it as equal to something like this. It's defined only at frequency value equal to 0. But right now I can think of this delta f minus f naught as frequency translated impulse function, such that it is somewhere at positive frequency. So it can be thought of as right shifted, right side translated impulse function at some other frequency, at some other frequency f naught, something like this. So this is the one that which I'm trying to represent in red color is the same impulse function, but the only thing is it's right shifted. So, and if I look at the other term, delta of f plus f naught is again impulse function. Again, it's an impulse function. Only thing is right now it's left shifted or left translated signal. So this is delta f plus f naught. So this is some negative frequency, negative f naught. Now, both these two signals are associated with what amplitude value? It's equal to half. Both are associated with amplitude value equal to half. So it's half over here as well as half. So in fact, if I were to write this cos omega t in frequency domain, it's half delta f plus f naught, and over here half delta f minus f naught. Where this is some negative frequency and this is some positive frequency f naught. So we know this. Now to this, if I apply Hilbert transform, so initially we had applied Fourier transform. After that, let's apply for Hilbert transform such that I'll get x cap of f. Now what is this x cap of f equal to? So anyhow, half I'll write as it is, the starting part, because that which is a constant. So then the next thing that I'm having here is delta of f minus f naught. So f minus f naught, what is this part? What's the frequency associated with this? Guys, I want some answers. Now tell me, this delta f minus f naught is associated with what frequency value? Positive or negative? Positive or negative? F minus f naught. All I'm asking is whether it belongs to right hand side of this 0 or onto the left hand side of this 0. Positive, positive. Yes, that's the right answer. That's the right answer. So it belongs to what? On to the right. Because while making this diagram, delta of f minus f naught, we had written it on to the right side. This is right translated signal. So this is positive frequency, and positive frequencies should be multiplied with what? For positive frequency, it gets multiplied by what? Negative j. So let's bring in negative j along with it. So it's negative j negative j negative j delta f minus f naught plus, what about this delta f plus f naught, whether it belongs to right hand side or onto my left hand side? Can I have some quick answers, because we are running out of time? Guys, I'm waiting for answer. My question is whether this delta f plus f naught belongs to right side or left side? Left. Yes, that's the right answer.
Left side.
So here, according to Hilbert transform definition, negative frequencies should be multiplied by what? Positive j. It should be multiplied with positive j. So here it's positive j delta f plus f naught. We'll have this. Now, out of these two, what I'll do is I'll take out negative j as common. I'll take out negative j as common, such that we'll be left out with delta f minus f naught over here. And here, because I'm trying to take out what? Negative j outside. I'm trying to take out negative j outside. So here, the sign here changes to negative delta f plus f naught so this is minus j by 2 delta f minus f naught minus delta f plus f naught. Now, just in order to bring this j onto the denominator, what I'll do is I'll multiply and divide it with j. What I'll do is I'll multiply and divide it by j, such that I'm having two j's on my numerator, such that I'll get it as minus sign j square divided by 2j delta f minus f naught plus delta f minus f naught minus delta f plus f naught. And over here, we all know that j square is -1. So -1 into negative sign, I'll have positive. So it's 1 by 2j delta f minus f naught minus delta f plus f naught. Now, is this equation, have you anywhere gone through this sort of equation? Is this equation familiar? That's my question. Is this equation familiar to you guys? Obviously, this is a familiar signal. I'm waiting for some answers in the chat. This is a familiar signal. This is a familiar signal, or a distant relative of yours. You have forgotten this. So this is nothing but cos omega t. Oh, okay, it's not cos omega t, because we started off with cos function, right? We start off with cos function. Cos function is what? Half. It's half delta f minus f naught, then plus delta f plus f naught. So what happens when I 90-degree phase shift cos function? I'll get it as sine. So this is sine omega t. So this thing is sine function in frequency domain. So this is in frequency domain. This is in time domain. The same sine function. The same sine function in frequency domain. So if I apply inverse Fourier transform, I'll get sine omega t. For time being, let's not do that. Let's not do that because right now we have just got equation for x cap of f. But what do I want? X double cap of f. We need to find it for x double cap of f. So let me apply Hilbert transform again. Let me apply Hilbert transform again such that I'll write 1 by 2j as it is. Now again, delta of f minus f naught is what? It's associated with positive frequency and this side is associated with negative frequency. Something that which is positive frequency has to be multiplied by what? Positive frequency should be multiplied with negative j. So again, I'll associate negative j over here and here positive j, such that now what I can do, I can take out negative j, that which is common for both the terms outside. Negative j, I'll take it outside, divided by 2j, and within these flower brackets I'll have delta f minus f naught, and here I'll have plus sign left because right now I'm trying to take the entire negative j outside. Delta f plus f naught. Now over here jj gets cancelled. Jj gets cancelled out and we'll be left out with what? Negative 1 times 1 by 2. All I'm trying to do is I'm trying to separate this negative 1 with that of this half. Delta f minus f naught plus delta f plus f naught. Now, what is this function? Now, I'll repeat my question again. Is this function familiar? What is this? Can I have some quick answers in the chat? What is this? No, it's not sine. Let me take you back. Let me take you back over here. Now, what is this? Half within the brackets delta f minus f naught plus delta f plus f naught. Is this the same function? Yes, it's the same function. So if I apply inverse Fourier transform onto this, I'll get it as cos omega t associated with what sign? Negative sign. So here we had x double cap of f. Here we had x double cap of f. And when I apply again inverse Fourier transform onto this, I'll have x double cap of t. So what is this cos omega t? We initially started off with this cos function, right? Cos function, cos omega t is nothing but x of t. So I can replace this cos omega t with x of t. Along with this negative sign. So this proves our property number 2, that is Hilbert transform of an Hilbert transform is the same function but associated with negative sign, and this is property number 2. This is property 2 of Hilbert transform. So that's it for now, guys. If you have not typed present in the chat, please do type present in the chat section. We'll meet in our next class. Till then, stay safe. Don't roam around. Stay at your home. So in this derivation, if you are having any doubts, you can ask me. If still we are having some less than 1 minute, if you are having any doubts, you can type it in chat, or you can send it via WhatsApp